So now that we have learned about the components of a solution and what causes a substance to dissolve at a certain rate, let's get more in depth on what happens within a reaction. My goal for you today is that you are able to describe collision theory and you're able to interpret solubility charts and curves. Before we get into the graphing section of this video, we need to talk about collision theory and its implication for chemical reactions. For chemical reactions to occur, a molecule needs to come in contact with another molecule and have enough energy to break that second molecule's bonds. Once that occurs, the atoms of the molecules will rearrange themselves and create a chemical reaction. The amount of energy that a substance needs to break the bonds of a molecule is known as the activation energy of the chemical reaction. If two substances collide and they do not have enough energy to match or exceed the activation energy, then the reaction will not occur and the molecules will remain unchanged. The collision theory explains many characteristics of chemical reaction. It is the idea that molecular collisions create chemical reactions, and it holds quite a bit of validity even today. Think about if I increase the concentration of a solute within a solution. Then there are more molecules of the solute for the solvent to interact with, which will increase the likelihood of the solute being dissolved. Also, if I increase the temperature of the solution, it increases the kinetic energy of the solvent, meaning that it is going to be moving around a lot faster, thus resulting in a higher likelihood of the solvent-solute interactions. Okay, so in the real world, solutions are never static. They are constantly moving and behaving in dynamic ways. Though it may be easier to view a chemical reaction proceeding in a one-way linear fashion from reactant to product, it is not the reality of how reactions occur. We do not go from two things reacting together to form a product. There are also reverse reactions occurring in which the product formed may eventually dissociate back into the reactants. Thus, the reactions are constantly going forward and backwards. What we visibly see, though, is what a majority of the reaction is doing. So if the majority of the reaction is proceeding in the forward direction and forming the product, that is what we can physically observe and what we are physically seeing. There is a point in a reaction in which the forward and reverse reactions occur at the same rate. For example, if three molecules go through a forward reaction at the same time as three molecules go through a reverse reaction, we would not visually see the reaction. This state is called equilibrium. Now that we know this, we can talk about graphing solutions. So let's graphically represent adding sugar to water. We are going to label our y-axis on the table as the mass in grams of the solute being dissolved in our solution. And our x-axis is going to be labeled the mass in grams of this solute added to the solution. So one is the mass of solute being dissolved, one is the mass of solute being added. We can see from our graph, as we add more sugar to the water will dissolve the same amount of sugar. This abruptly stops and levels off at a point though. Even though we add more sugar to the water, the amount of sugar dissolved doesn't change. So if I'm labeling the graph, I would say the increasing slanted line that would begin our graph would represent an unsaturated solution. So this is where stuff can be dissolved. More sugar you add, the more it can be dissolved. The point in which the slanted line abruptly levels out and the amount of sugar added equals the amount of sugar dissolved is the point of saturation, which means this is a solution in equilibrium. The remaining leveled out portion of our graph shows us that no matter how much sugar we add, the amount of dissolved sugar will not change. This means the solution at this point is supersaturated. Another type of graph in which we see is solubility curves. Solubility curves show the solubility relationship between the temperature and the amount of solute present. The basic information we gain from this graph is how the level of saturation changes as the temperature and amount of solute changes. For example, we can graph out the solubility curve for potassium nitrate, KNO3. Anything above the graph line is considered supersaturated, while anything below the graph line is considered unsaturated. That means the line itself is our equilibrium point, so anything found on that is at equilibrium. If we had 30 grams of potassium nitrate at 20 degrees Celsius, that would be right here. This would be above the solubility curve, so 30 grams of potassium at 20 degrees Celsius would create a supersaturated solution. But what if we had 40 grams of potassium nitrate in an aqueous solution at 60 degrees Celsius? This data point would be here, and it would be below the solubility curve. Because of that, this solution would be considered an unsaturated solution, and you could add more potassium nitrate to it, and it would dissolve. Finally, if we reach any point on the line, so if we graph out a point and it ends up being right on a line, that solution is in equilibrium. Okay, that's all I got with the graphs for you. Hope this helped you out and gave you a better understanding of the dynamics of solutions. Keep up the good work and see you next time.